newspapers, right? Not only scientific journals, but everywhere. Then is even 2025 is the quantum year. And the reason is that there is a growing interest, right? A large funding also. So all seniors are always worried about how they will fund their research. So there is a lot of money going to quantum information, quantum computing, quantum technology in general. And you will hear more and more this year because there will be many activities at CERN and around Europe. So quantum computers are on everyday life right now talked about. They have we have great expectation from quantum computing, which we don't know yet, right, if it will be fulfilled or not. We are all waiting and working in that direction. But I mean, the idea from a physics point of view, so not engineering now, but really physics, is like you know, we learn what is the physics regulating an atom, so a scale of an Armstrong, let's say. And what we are trying to do, somewhat, that's a simplified vision that I have, we are trying to bring these phenomena which live naturally at the Armstrong scale up to, you know, our scales, meter scale. Right? There are experiments of teleportation, which is a quantum phenomenon, that go on, you know, over kilometers. Quantum cryptography now is also ranging kilometers and an established technology. So all this quantum trend is really trying to bring the quantum mechanics, the aspects which are more subtle about quantum mechanics, to use quantum mechanics as a resource to do something that without it we could not have done. Right? Quantum computing is one example of that. There is another direction that where we are going, mostly theorists, and this is mostly like string theorists or formal theorists that try to understand how to put together quantum mechanics with gravitation. And then what they are studying are like black holes, or you know, imaginary black holes, let's say, mathematical black holes, where you check how the information goes, how comes if information is lost in a black hole or not. This goes under the name of it from qubit, is a large community in theory, in theoretical physics, that is trying to study that, trying to also, again, as I mentioned, try to somewhat understand how gravitational interaction works at very small scale. So what I'll be talking today is something in between, is the idea that we try to use quantum mechanics phenomena, purely quantum mechanics phenomena, as a resource to investigate one of the goals of the LHC, of the high energy community in general, which is to understand fundamental interactions better. So fundamental interaction for me means standard model, elementary particles, quarks, leptons, all the stuff that we study at LHC nowadays at CERN, or in many other experiments that work at different energy. And lower energies, like Bell or fixed target experiment, or even at much higher energies, like neutrino observatories, like IceCube or other experiments that detect gamma rays or particles that come from space, which have very high energy. So there is a big community, as you know, which is called high energy physics, whose aim is to understand the fundamental interaction, the particle and how these interact. So the goal, right, the idea of today is to try to use, and I repeat, quantum mechanics phenomena to study that. So I also have a personal motivation or a social motivation. As I tried to tell you, there has been a growing interest. So these are the citations on the first paper in 2020, predicting entanglement in TT bar production at LHC, which is what I will be talking about. And then this is the number of papers coming out in the following years. Okay? So far is an exponential, it's a very steep rise of interest in the community. I don't know in 2025 what will happen, but so just to give you that there's been an avalanche of these works following up this first proposal. Then, not only in application at LHC, but as I will try to mention at the end, there is really a broadening of the scope and the idea. So I really will try to give you a gist of what are the questions that now people are asking. Okay? And then there was a big change in November 2023 because these were the first evidence of detection of entanglement and very high energy, again, which we will be talking about today. So my personal motivations, well, we discussed with Giovanni this morning. So what people doing quantum field theory are also doing quantum mechanics, and therefore, of course, so what we give it for granted, but we never think, well, we not often think with this mind either, right? So what is our tool with which we do all predictions, but we're not often thinking what it means from an experimental point of view. Then there is meaning. Meaning is that I would like to understand whether quantum information can give a different angle on studies that we are doing, and vice versa, if the fundamental interaction that we know of can teach something to quantum information. This is an open question. And then there is value, right? So one example is, like all experiments of quantum computing and so on, basically deal with proton, electrons, and photons, right? I mean, all quantum computers are based on phenomena and low scales, where we know that weak interactions or strong interactions are not playing any role at that level. While the standard model, right, in its complexity or beautiful simplicity, has a number of features that go well beyond the way that proton and electrons interact at the Armstrong scale. So there might be much more that we can learn about these interactions, or these interactions can teach to possible ideas in quantum computing. And then, of course, there is the user motivation in our field, which is to explore. And our field at higher energies has two goals. One is to fully understand what we know, like the standard model. We have not fully explored the phenomenology of the standard model. This is what I call as standard model uncharted territory. And then, of course, there is the Holy Grail, which will be to have, convincing sign of new physics from collider experiments, which, again, we don't have right now. So the question, again, is, can quantum information help in charting the standard model and also discovering something beyond the standard model? Try to argue that it might. Okay, so the plan of this colloquium is very ambitious. Okay, so not for me, but for you, in the sense that I will be trying to give you a condensed lecture of 10 minutes of quantum information, giving you the lexicon and the idea that I will later use. Okay, so basically, you only need to know quantum mechanics, really. So who has taken a course in quantum mechanics? I hope everybody. Us? Okay, most of it. So you can talk to your neighbors if they don't understand something about quantum mechanics. Okay, so let me try this crash course on quantum information. Ready? You fasten your seatbelt, right? And you try to follow, right? So this is the time to pay attention. Otherwise, you're going to be lost after the 10 minutes. Okay? I'll go fast also. Okay, so quantum mechanics. So textbook, we have a wave function like that describes a system, a quantum system. This wave function satisfies an evolution equation, which is a Schrodinger equation. And the way we get the results out of that is to compute expectation values of self-adjoint operators on given state. Okay? So the way we link theory and experiment is by identifying an observable with an operator and averaging, right? Calculating the expectation value on a given state C. There are some conditions, right? And the C has to be normalized, or you normalize it if it's not. So this is the way I was taught quantum mechanics in my class a long time ago. Right? That's all of it. But there is a bit more, right? There is an extended framework which we can use. We can also learn it normally, right? Which is that of the density matrix. Okay. So instead of using the pure, so these are called pure states. Okay. So wave function. And then there is a way of describing quantum mechanics in slightly a more general way. So the way that we are normally taught about this is that if you have an open system which talks to an environment, right, normally in experiments on, you cannot get normally pure state. What you get is an ensemble, a statistical ensemble of pure states, which are not a superposition of states. Our statistics are quantum independent, right? And they're not coherent. And these states, J, right, there are several of these states J. You see that they are incoherent from the fact that if you change the phase of this state, this rho does not change, right? Each phase, I mean, rho does not depend on the phase of each one. So it's an incoherent sum of states, and each one comes with a given probability Pj. Okay, so it's a statistical ensemble. So you can formulate quantum mechanics in the same way, right, by using this pure or rho state. Rho is an operator. It satisfies an equation of evolution. And if I want an expectation value for an operator, instead of taking the average value of A, I take the trace of A over rho, which is basically, right, the weighted probability, the weighted expectation value on each one of the states weighted by the probability. So the normalization condition goes to trace of 1. And now one point which is important. Now the rho is general, that if you have, you can always describe with the rho matrix a pure state. If you only have one P, right, this is pure, and therefore your state is exactly pure. So how do you distinguish between the two? These one generically are called mixed. This one is pure. And there is one operation, very simple, that you can do to know if a state is pure or mixed. You calculate the trace of rho squared. If a rho squared is 1, the state is pure. If the trace of rho squared is less than 1, the state is not pure, it's mixed. Okay? Okay, very good. I see nodding. Now we add one level. So why rho is useful? Well, today is useful because we will realize very soon that if you have a system which is composed, having pure state to try to describe a system made out of two subsystems is not enough. Okay? So you would go out immediately. So if you have a system C, which is divided in two, okay, and these two subsystems are quantum, so you can easily prove that typically if the mixed state is pure, the C, A, and B will be mixed. Okay? So it's not a subsystem, don't maintain the property of pureness of a global system. Okay? So you are obliged to use a rho whenever you talk about subsystem. So now, if you have a subsystem, A and B, you can write a pure state as a tensor product. This we'll also learn. This is a pure state. There is only one for each substate. Or a generic state, pure, will be the sum over all combinations. And this is called, in general, entangled. Okay? So out of this generic state, when you can write it in this way, so you see that it's diagonal now, right? So each subsystem has a rho, but the sum is the same index, not two different indices like that. So it's the sum of direct products, like this one. This one is called, by definition, separable. Okay? Separable, in our mind, so what should remind us, kind of classical. Then the two systems are not correlated. Okay? So now, the definition of today, if a system which is composed is not separable, then is entangled. Okay? And entanglement is one of the keywords of today's colloquium. Okay? So the entanglement definition is by negating, right? Is by negation of separable. Right? Is what is not separable is entangled. Entangled means there is some form of quantum correlation between the two subsystems. Now, if two subsystems are entangled. So if a system C has two subsystems that are entangled or not, depend on the subsystem, not on C. Okay? So entanglement is a property of the subsystem. So one typical example is the hydrogen atom. The hydrogen atom is entangled if you use a coordinate, which are the two particle coordinate, the nucleus and the electron. But if you use the center of mass coordinate for the system and you somewhat diagonalize the Hamiltonian, then it's separable. Okay? So the same system can be entangled or not depending on what are A or B. So it's not a property of the system, it's a property of A and B to be entangled or not. Okay, so there are some theorems, and I'm not going to the detail of the theorems, of course, and there is one that's called Schmidt decomposition, that basically tell you that if you have a C state, a C system in a pure state, then you can tell a lot of things about the subsystem. But in general, if the state is mixed, it's way more difficult to characterize the level of entanglement of the A and B. Okay? So there are a number of theorems here. So one of the things that it's important to explain that this theorem tells basically that when you look and you have a pure state, general, when you look at the subsystem, in general, they are mixed. So the more entangled is a system AB, right, globally pure, the more mixed are the subsystems, which is, like not a contradiction, but it works the other way around, okay? So the pure system, the more entangled it is, the more mixed are the subsystems. Okay, so these are, you can show in two lines, right? This is a small theorem. You take a Bell state, which is maximally entangled between two qubits, and then you check what is the state of A or B, is completely symmetric, and you see that the raw matrix, so the density matrix of the subsystem A and the subsystem B is maximally mixed. So it's maximally scrambled, right, with that maximal entropy. Okay. So this is something that you have to keep in mind. It works the other way around. The more entangled is the system, each subsystem is maximally mixed. It's not pure. Okay. So now we need another concept, which is called concurrence. So we need a measure on how much a system is entangled. Not a system, but the set of A, B are entangled among them. So what do? We compute the trace square of the subsystem. Because I told you that the more the subsystem is mixed, right, the more basically entangled will be the pure state globally. So basically, the smaller is this concurrence, the less is entangled. So concurrency equal 1 means maximal entangled. Why? Because the trace of rho square is 1/2 if it's maximally mixed, and therefore this number is 1. Okay? So you look how mixed are the subsystems to tell how entangled is the A and B system. So this works only if you have a pure state globally. So how do you know if a system which is mixed is entangled? It's a difficult problem. In general, we have solved it exactly only for 2 qubits and 1 qubit and 1 qubit. We don't know a general solution for more, right? I mean, it's hard to detect whether a system is entangled or not. It's an NP complete problem, actually. So computationally, it's difficult. So people in the last 30 years have developed theorems, techniques, criteria, and so on, to know whether a system is entangled or not. It's not an easy thing to know. So people have and come with criteria. This is one of them, is a mathematical one. I only want to mention this because for 2 qubits, which is all I will talk about today, this is a necessary and sufficient condition. So if you know that this criterion is satisfied, then you know the system is entangled. Okay? So we have a marker of entanglement. We have a system, we compute the rho, we apply this criterion, and then we know immediately if it's entangled or not, even if it's mixed. Okay? Is that clear? Okay, very good. So then the other thing I need to talk for 2 minutes is what we learn in quantum mechanics classes, is the famous EPR or Bell inequality. So I don't go now into the proof is on the slide. It's very simple, right? You have Bob and Alice. They make 2 measurements with 2 different axes here of speed, 2 on the other one. They're space-like separated. They don't talk to each other. Then they build a correlation, and you can show that a combination of these expectation values has to be less than 2 if the spin is a real, right, is a property which has a reality content, okay? So it exists before the measurement. Then you show that this relation has to be smaller than 2. Now, for what concerns today, we have to remember 2 things. First, Bell inequalities have nothing to do with quantum mechanics. You can define Bell inequalities measurement independent of quantum mechanics, so you can test them against quantum mechanics or not, but somewhat are independent. Okay? Quantum mechanics can be true or not, or maybe there is another theory, and then Bell inequalities, this proof holds. Okay? It has nothing to do with quantum mechanics. And the proof is here. The other thing is that quantum mechanics violates it. So there are elements which are elements of non-reality in quantum mechanics. Okay? Now, for what is important today is what is shown in this slide here. My last slide of the crash course. Okay? So this I didn't know at all about this before studying, right, a few years ago. So for pure states, so if you have a wave function of a system, so saying that is separable is complementary to saying that is entangled, and entanglement is equivalent to Bell violation. Okay? So if you have a pure state global, if you see that the system is entangled, will violate Bell inequalities, and vice versa. They are the same thing, but only if it's pure. If it's mixed, it's not true. So Bell inequalities are stronger than entanglement. So the system could be entangled, but not violating Bell inequalities. So Bell inequalities within quantum mechanics mean stronger entanglement. Okay? And you see from this slide that there are different gradings of correlations. There are even correlations which are less than entanglement, but still not classical correlation. Okay? So when you have a mixed state, you have a number of difficulties in trying to identify what is the level of correlation. It's very difficult, and there are many theorems, many proposals for many systems to try to measure or to characterize the level of correlation that a two subsystem can have. Yes?
So quantum mechanics leads where Bell violation is the rest. So there is some entanglement outside quantum mechanics?
No, what I mean is entanglement. So before I gave a measure of quantum mechanics using concurrence. And I told you, of entanglement measuring concurrence. So concurrence can be from 0 to 1. So 1 means very much entangled. 0 means not entangled. So it's a continuous level of a possible entanglement in a system. What I'm saying is that for a given system, I'll show you in a moment, the the range where the system of rho, where the system is entangled, is like this, between 1 over square root of 2 and 1. But when the quantum system violates Bell inequality, it's much smaller. It's a subset of where the system is entangled. So Bell inequalities for a pure system are equivalent to quantum mechanics. Bell violation is equivalent. But for mixed system, it's not equivalent. It's stronger if you interpret Bell violation in quantum mechanics. Okay? So when I will talk about Bell inequalities, I will only talk in this language. So if a system violates Bell inequalities for me today, I'm only talking about quantum mechanics and not checking, other hypotheses like local, observable, whatever, right? Strange. I'm only using quantum mechanics. But for me, it means that as a strong entanglement. Okay? Okay. So now the crash course is over. You have the lexicon. You have to remember concurrency, mixed state, rho, and so on. Okay? So now we go to a system that we know very well and the LHC. And this system is a pair of top, anti-top quarks. So there are many, you see, these are the papers in the last few years. There are as many papers on other systems, right? Like X indicates WW, ZZ. So for example, in W, you might remember, a W is a vector which is massive, so it has 3 polarization, so it's a Q trait in quantum information. So if I study the correlation between the spin of 2 W's in the Higgs decay, I'm studying Q trait correlations, for which these theorems don't hold, for example, the one I was telling you. So it's much more difficult and even interesting. So why tops? So now we go back to high energy physics. So I'll give you the essential. Tops are the heaviest particle that we know, elementary as far as we know, in the stellar body. They are the 6 quark, right? They are very massive. They are 172 GeV, so they weigh 172 times the proton, more or less. And they have a special status. Why? Because they are only quarks that are heavier than the W boson, and therefore their decay, their lifetime, is very short. So they are produced, and LHC mostly, through strong interaction, through gluon fusion or quark-antiquark fusion, most of the time in this way. So they are produced strongly and they decay weakly. Okay? So it's a special thing. Okay? It's a special particle. They decay almost immediately before the strong interaction can kick in and bound the top into a meson, right? Like in the B quark or the charm quark. The charm quark are also produced, but somewhat a quark from the C gets together and you get a D meson or a D meson and so on. The top, before they can do that, it decays. And due to this, it does not hadronize. And the other thing that it does, it decays so quickly that what happens, and this is another coincidence due to the weak interactions, what happens is that it decays to be W lepton neutrino, and magically what happens is that the direction of the lepton actually is 100 correlated with the direction of the spin of the top. Okay? So at LHC, we cannot measure the spin of the top directly. We don't have polarimeters like Bob and Alice. However, we measure the direction of the lepton which comes from the decay, and this lepton is 100% correlated. It means that statistically it's correlated. It doesn't point always to the direction of the spin, but statistically is 100% correlated to the spin of the top. So we can use and reconstruct the lepton as if it was a polarimeter for the top and the anti-top. So this is called quantum tomography. This I don't have the time to explain, but in your mind, imagine that the decay is like measuring the spin of the top. Okay? We are using a proxy for the spin, which is the lepton, and the charged lepton, you can ask to any of your colleagues working in the LHC, is the best all over observable that we can even imagine, because it's very clean, and we know where the lepton goes, right? We can measure the momentum, the energy, everything. So this is very, very useful, okay? So this is a picture of what happens. The top and T-bar protons collide, a TT-bar is produced. And in the central mass frame, they fly back to back, and then they decay. Okay? In the beam pipe, right? I don't see the top in the detector. And then I have the two directions of the lepton, and what I have to think, how I have to think about it, I think about Alice and Bob. Okay? So that's the whole thing that we need to understand. We have a kind of an EPR experiment now, when the top and the top fly, then they decay, and in the decay, we are measuring the spin, like a polarimeter. From this, I build a correlation function on where the spin go, if they always go like that, or they are more often like that, and so on. Okay? So we build a correlation matrix. So in order to do that, we need to build two reference systems. I'm not going into detail. We have to compute angles. So we do 9 plots, two-dimensional plots of these angles, and then we extract this coefficient Cij from the plot. So this is something that we do normally in LHC. It's nothing mysterious. And finally, right, I go back to my quantum mechanical system, and I write the most generic density matrix for 2 qubits. Right? I'm looking at the spin of the top. The spin is 1/2, 2 qubits. And this is the most generic rho that I can write using the sigma matrices that we learn in school. And then the coefficient in front of these structures are the average. So this is the average polarization, which are 0 and LHC. And then this matrix here is the correlation matrix. Is the number that tells me that the spin of the top are not random. Okay? If they were random, all these numbers were going to be 0. If there is a correlation, these numbers are not 0, are not equal to 0. So then what I do, I calculate my markers of entanglement and my marker of Bell violation. How I do that? I compute the eigenvalue of the Cij matrix. Okay, I build 4 of these markers of entanglement, and then I can show that if any one of them, at least one, is less than -1/3, the system is entangled. Okay? If it's even more extreme, okay, if this combination is less than 1/√2, then the system violates Bell inequality. Okay? So it's a subset again. It's a very much entangled system that violates Bell inequality. So this is the proof of the theorem. I leave it there if someone is curious. But just to show you that you can prove all these statements in 2 pages. Okay? It's a quantum mechanical exercise. Okay, so basically we have 2 markers, and one, remember, I have this D marker. So the other thing you have to remember that you have 2 spins. So what are the total angular momentum state of 2 spin 1/2? There are only 2, right? Either is in a singlet or is in a triplet, in a vector. And the vector has 3 components, right? Up, 0, and down, right? So out of 2 qubits, you can do 4 states. One is a singlet, and the other 3 are in a vector representation. Okay, very good. So what is the result, right? So first we run a Monte Carlo. We compute the level of entanglement. These are like concurrence. So you see, this is the angle, cos theta, with which the top go out. and this is the speed with which they go out. And the color, the more red, is the more entangled. So the thing you see immediately is that there are regions of phase space for the two tops where the tops are not entangled at all. And there's a white region. Why? Because the system is mixed. Why is mixed? Because there are several contributing diagrams and processes, so it's a statistical ensemble that have to have some non-trivial correlation to beat the minimum of entanglement. And this happens only at threshold, here, or at 90 degrees and very high PT. In fact, at threshold, the PT bar are in a singlet of speed, and at 90 degree and very high momentum, they are in a triplet of speed. This you can calculate from first principle. So this is a GG channel. So the GG is not pure by itself, it's mixed automatically, while the QQ bar is always pure, but the level of entanglement varies, right? And they are only entangled in very high PT. So if you know a bit of collider physics, a very high PT is very hard to produce tops and high invariant mass because it costs a lot of energy, and this is suppressed by the partial distribution function. But we have a lot of tops fit pairs at threshold. So people have looked, okay, let's start and look at this correlation, which does not depend on the angle, but it depends only on the TT bar being produced very slowly, right? With a little bit of speed, and they're very close, right, at threshold. Okay, so we go back. This is our paper of 21, and then we went there and we calculated, we predicted if LHC was going to see entanglement, and we said, sure, theorists, right? For theorists, it's always easy, right? When they run the Monte Carlo and they see 5 sigma, then it's done. Life is not true like that, but well, we convince ourselves that this is feasible. But in the end, in 2023, 24, this was proven, as I'm showing you. And then we also said that high PT was possible, but much more difficult. And these are the results of Atlas and CMS of the last year. So let me read you the plot, because this is important. So on the x-axis in Atlas, there is the invariant mass of the TT bar pair. So this bin means the TT bar go very slowly, the invariant mass is very small, and then it's faster and faster, okay? So my theory predicts that the tops at threshold, my marker V, is less than -1/3. They are entangled. If this number is less than 1 -3, is entangled. And now you see the theory prediction here from our of the best Monte Carlo we had, and then the experimental point here. So what do you see? Well, you see that Atlas observes entanglement for the TT bar pair. So now what about CMS? So CMS has always to do something different. So instead of plotting D on the y-axis, they plotted D on the x-axis, right? So the plot looks different. Okay, so but D is the same, right? So now D is on this side. So less than -1/3 is here. And instead of plotting the invariant mass, they're only plotting the bin and the light loop. And what you see is that they also measure D less than -1/3. So the measurement is the orange line. So if you pay attention, so both of them see entanglement. Okay, it's all good. But what do you also notice? There is another thing which is striking, somewhat, not significant, but striking in both plots, which is there is more, thank you, there is more entanglement than what predicted by our theory models. Because both CMS sees more entanglement, right? It's not really significant, because, well, above all because there are no uncertainties on theory here. So, but here there is, right, somewhat, right? There is a likelihood. So there is more entanglement, both in SMS and Atlas, than predicted. So keep this in the back of your mind, because we will use it in a moment, okay? So I leave the suspense and keep this in your mind. So let me go now, look at how could we test entanglement at the level of violating Bell inequalities? Very hard. This is going to be hard because possible, maybe, but the region in phase space where this is clear is tough, very high PT, very few events. This is going to be tough. I hope it will be done, but it's not easy, okay? Okay, so now let me go to the final part now. So we know that TT bar are entangled. This is a prediction from the standard model. We are testing the prediction with the data. So the question now is, so what? Right? Okay. I mean, it looks partially interesting, right? But I mean, what do I learn, right? And what could I learn from this, or what I do with this? Okay. So now we go back to what Bill Wouters said in '93 when they start talking about these quantum algorithms, right, for quantum computing. What he said was, I don't want to study whether the world, the universe, satisfies quantum mechanics. So I don't want to do something for quantum mechanics, but I want to ask what quantum mechanics can do for me, right? So I want to use quantum mechanics as a resource, okay, as a tool to do something they cannot do classically. So that's the spirit I want to explore with you now in the next 10 minutes. So all of us, basically, are interested in finding new physics at the LHC. So the natural question is, can we use is any reason, any feeling, any application of quantum observables that are more sensitive than our best observable that we use at the LHC to test fundamental interaction, that could be used for that? It's a legitimate question. The answer might be yes, I mean no, I don't know. Okay, so let me explore this. So at the LHC, nowadays, we are using two methods to look for new physics. One is look for new resonances, like easy peasy way, theorist point of view. So that you look for resonances, like which will be the smoking gun of new physics. You find a new state which is not in the standard model, done. You go to Stockholm, you are happy, right? Then there is another way, which is to try to make very precise measurement and check whether there are deviations which are correlated in a predicted way. So let me go into this first. So the way we do this is called effective field theory. I'm not describing the details, but basically what we do is to deform the Lagrangian the standard model with other interactions, right? So we are not at this level, right? We don't have animals in full shape. We are not in the sphere level of the standard model. We are somewhere in between where we are looking for deformation of the measurement that we are checking, right? So we make 100 measurements and we check if all of them sit on the standard model or not, basically. So now the question is, imagine that there are this deformation in TT bar. Do we gain anything by measuring the entanglement in TT bar as a sensitivity to these new terms in the Lagrangian? So this is the ratio plot, and it shows the darker is the region, the more sensitivity you get. And this plot shows that in the transition region, you have a lot of sensitivity to EFT. So what we proved is that in this case, for TT bar, there is additional sensitivity that you can gain if you use this spin correlation observable, both in the decay, like this is one of the operators, the chroma operator. I'm not going to detail, but also in the production. Okay, so there is some power in breaking the degeneracies. Also, we have found something peculiar, which we don't know why, right? But it's not mentioned now. But so what we find some kind of some rules at the level of dimension 6, where entanglement is, so the deformation of the standard model at dimension 6 are protected by maximal entanglement, and therefore there is no effect at threshold. So there are cancellation, like which don't look by chance, and then there are no modification of entanglement at dimension 6. This we don't explain, but it could be suggesting something deeper, which we don't know right now. Then the other thing we can do, always in PT bar as an example, is say, well, maybe there is a resonance, right? There is a new state, phi, a scalar, a z prime, or two stops, then decay in PT bar, which predict different correlation metrics. So, for example, for phi, if it's a pseudo-scalar, then I predict maximal entanglement at threshold, okay? If it's a pseudo-scalar. If it's a scalar, it will be a 3p0 state. So it's a L equal 1. It's not an S state, it's a P state. But again, there is some kind of different pattern of entanglement with respect to QCD. For Z prime also, we calculated the correlation matrix, is not shown here. And then for stops, is interesting because the stops are scalar partners of the top. So when they decay, they don't transfer any spin information because they don't have any. So the top are fully uncorrelated, but they are maximally polarized. So it's completely the opposite of this case here. It's very different from the standard model. So in this case, the sensitivity comes from not seeing any quantum correlation in PT bar if they were produced in SUSY, but they are very much polarized by themselves. Very different from the standard model. So it's interesting. All of this was known, by the way. It's not new, but it's just phrased in terms of quantum observable. So now, what I'm doing, I'm comparing this in a simplified scenario, the sensitivity of this new observable with a normal way you will discover a resonance. So how do you discover a resonance at LHC? You do an invariant mass plot, and you check whether there is a peak, which is the bright linear peak of the resonance. Okay? So this is a normal search for a resonance at LHC. So we compare this, which is the black line, which assumes some resolution of the order of the experimental one in the reconstruction of the TT bar pair. The black one is the pure invariant mass scan, while each of the color is one of the quantum markers, one of them, not combined. So the lower is the curve, the better is your sensitivity of the coupling of new physics to your TT bar pair. Because your coupling goes down means that you are more sensitive to smaller value. So the best is low. A low curve means that you're doing better. Okay, so what we do, how do we interpret this plot? We see that the black for a Z prime, so for a vector, and for SUSY, right? So mostly for a vector, the invariant mass search is better. So you don't gain much from the quantum observable. For the stops, is not fully true, right? Because they are very, very close, right? A high invariant mass, they are better, and then if you combine them, you probably get better. So they are competitive, let's say, okay? Which also was known somewhat. But now you look at the scalars. And the scalars, you here a scalar, vector high masses, pseudoscalar, basically always better. So the pseudoscalar state is the one where, if you were looking for new physics in TT bar and look at this observable, you should bet on in using, right? So if a pseudoscalar is there, you should be using this spin correlation observable because you have maximal sensitivity by combining with the increase of the cross-section given from the peak. Okay, so now what do? We go back, right, to our tension, right? We go back to our attention with new tools, right? Because now I say, well, maybe I can explain these axes here by saying that there is a scalar state at right there at the threshold of TT bar production. Okay? So now you ask, why the hell there should be a pseudoscalar there, right? I mean, okay, pseudoscalar from a two-doublet model or so on can be anywhere. But, you know, like, who orders that just there, right, to help? And does it help, really? And the answer is that we forgot something, actually, which has nothing to do with beyond the standard model. So before going into the DSM pentagon, we should go into the uncharted SM territory, right? To be fully sure that we don't are misled. Okay. So what did we forget that from the standard model there? Well, what we forgot in our Monte Carlos is to include the toponium. Okay, so what is toponium? So not everybody agrees on the name, but I don't care. Okay, so let me call it toponium today. So I told you before that the top decays before it hydrolyzes. Okay? But there is one exception. An exception is if the top is produced together with an antitop and they are very close in phase space. Why? Because if the top and the antitop are close enough and they are in a color singlet state, so this we learn in a QCD class. I don't know who is teaching QCD here. But you learn that in QCD, in a strong interaction, if two quarks, quark and anti-quark, are in a color singlet state, are attractive, like a quark and anti-quark for QED. If they are in a color octet state, they are repulsive. This is a property of non-abelian gauge theories. Okay. So if you produce a TT bar very close, what happens really is that they have basically just the time to say hello to one another, right? To exchange one gluon. By the time they have exchanged one gluon, one of them decays. Okay? So when one of them decays, well, it's half time of the time that takes for one to decay. If we have two, so the probability for decay is twice. Okay? So the lifetime of toponium is half of the time of a top. If you do the computation, the numbers magically come out like they do classically. They do something like half a turn, and then one of them decays. So I normally say that it's a tragic love story, right? It's like Romeo and Juliet, and by the time, you know, they say, ah, and then one of them dies, right? And then it's a tragic love story. Okay. So remember, TT bar pair, for QC, you build the potential. The cool thing that we forgot about it, but we can compute everything out of it. I mean, we didn't compute yet all the orders, let's say, but I mean, it's fully computable, right? I mean, there is not, the regime of this bound state is perturbative. We can solve the Schrödinger equation with the potential, which is, you know, perturbative and so on. We know everything about this guy. We know the spectrum. We know how long it lives. We know how varied it is. What is the other state, how far it is, and so on. We know everything. So the only thing we need to do is to add it to the Monte Carlo, which was not done. Okay. So of course we did it in a, not me, but people did it in a rush, and therefore we didn't do the best of all possible work. But what we did, we had predictions from 2008 about what a peak of this toponium would look like in TT bar. So this is from very good colleagues of ours, from Agivara and company, very, very well-known people. And I personally remember when I saw this paper in 2008, which attracted my attention a lot, I just thought we'll never see it, right? I was one of the things that said, okay, it's cute academic work, but we'll never see it because it's too small, right? I mean, this is an opening of the threshold. Cross-section too small, the resolution is too large, no way. And then after 17 years, so this is the model that we used. So we took the computation which are N, LO in E plus E minus by Benek and company. So we know this super well, right? People went ballistic on this because this is the way that we will measure the top mass at 20 MeV and E plus E minus collider when we will have them. So this is a very important phenomenological reason to run E plus E minus and the Titiman threshold. But then what we did, we tuned our simplified Monte Carlo onto the exact computation. So it is a green line and then our approximated result. So you see that our simple model reproduces the NLO and NNLO computation very well. And then we use this model to predict how V is changed by adding, right, the toponym state. So even if the cross-sectional toponym is not so large, D, the variable D, is greatly affected in the region around the threshold. So that's where the sensitivity comes, even if I'm integrating over this region with a large, quote-unquote, mean. And now the CMS added the toponym model to their analysis, and then you see by eye that the predictions now move again, right? At this level, they were not yet significant, but they move in the right direction, but more importantly, they move of the right size also. Because as I said, there is no free parameter. All is fixed. So it just needs to be added, and then you see that this brings it back to a reasonable number. So now we have been promised the updates in Moriond, but Moriond QCD I think is next week, or I don't know, but it will be either this week or next. We will see the new results, most probably, with an update on this. Okay. Okay, so I'm concluding. Sorry, I'm a little bit late. So what else? Well, there are many studies. This is a summary slide taken by a colleague of mine from Atlas, Federica Fabri, who has been collecting all the studies that are going on in Atlas and CMS nowadays based on this observable. And then I made another slide complementary to this with all the theory paper that have been going on. So I really, I give the slides to Simone, but if you want to look at the question that people are asking, and they're very, very interesting, okay, which go beyond what I'm showing today. I'm just picking up one of them on the right here. Jesse Taylor from MIT have written in November a paper suggesting that by using entanglement as a dynamical principle, you could have a constraint on the CKM matrix. So on the way the weak interactions are structured in the CKM. So you can use entanglement and symmetries from entanglement as another principle to constrain the form of interaction. This is an old idea, actually. José Latorre and Juan Rocco and Luca Rottoli had this idea in 2017 already. And they found, for example, that you could constrain theta W, the Weinberg angle, by using this idea of minimizing or maximizing entanglement in a generic scattering amplitude. So there are works also by Kaplan trying to relate maximal entanglement possible in a system with the symmetry of the system. Very bold ideas, which I'm not talking about today, but people are exploring in a very intense way. So this is my summary. I think you got the idea. I repeated myself a few times, but I just want to really to transmit then there is excitement, there is opportunity from both experimental part and theory part, and what I learned personally by looking at fundamental interaction with these quantum information glasses is that like things that we see every day look different from this point of view, and in a very stimulating way. So I really, invite you to have a look if you have the time. Thank you very much.
Thank you, Fabio. Questions, comments?
So, first of all, thank you very much for the very nice talk. I have more a curiosity. So, historically, one of the major concerns in the experiments related to testing the Bell inequalities was the problem of loopholes.
Yeah.
What the status here concerning this point?
Yeah. Thank you very much for your question. So, my worry is the same. I mean, so that's the reason why I try to phrase the Bell inequality as an extreme entanglement state within quantum mechanics. Today, I never thought about testing or using PT-bar to test quantum mechanics. Okay, so the opinion in the small community which I was showing today, in this raising of number of citations on, which is about 50 people, people have different interests and different opinions on this. Okay, so this is like a warning. So now you ask me, I give you my opinion, but I want to tell that people have different opinions about that. So my opinion is that testing Bell inequalities with PT-bar is not going to help us very much, because the number of loopholes which people working in the field, which are experts of this EPR and tests of Bell inequalities at low energy, have discussed in the last 40 years, basically all loopholes that we're worried about affect PT-bar. Okay, not all, but somewhat some of them. So I'll give you one or two examples just to frame my comment. So I told you, right, that Bell inequalities somewhat will be hard to test here, our prediction. So you ask about if the state at threshold is so entangled, why don't you test Bell inequalities there, right? That's a natural thing to do. But then you realize that the B and the two tops are going so slowly at threshold that they are not space-like separated most of the time when they are decaying. And space-time separation is one of the necessary conditions for testing Bell inequalities. Okay? So you have to have in a region of phase space where they fly far apart, then at least in the standard model, they decay independently. When one decays, it cannot have the time to tell the other one to decay or vice versa. You see what I mean? So, and this happens only at high PT. The other problem that we have with Bell inequality is that in the Bell experiment, we have polar emitters, and the spin is measured exactly, so to speak, and this time. In PT-bar, we don't have a measurement of the spin in polar emitter. We do this quantum tomography a posteriori on a statistical basis, okay, not event by event. And while in the Bell inequalities, you're doing it event by event, not after. So, I mean, these already are 2 points which somewhat are intrinsic, right, in the problem. Right? So, for PT-bar, I'm not sure, but there are papers like our collaborators in CISA. Marco Fabbrichesi has written a paper about Bell inequalities violation in B J psi 5. They done their analysis, and from the spin correlation, they are in a regime where they test Bell violator. So it depends a bit what is your take. If you are really interested of testing quantum mechanics, or you're really interested in using quantum mechanics to do something else.
More questions or comments?
So there is a long standing small deviation in the PT spectrum of the TT bar pair in almost all Monte Carlo generators.
Right.
Can the missing toponium explain this, or it's maybe a too little effect, or maybe in a wrong kinematic regime?
Well, there was an invariant mass. I mean, this thing of the invariant mass separation was there since some time. The TT is a shape issue.
Yeah, it's
right.
or
The shape is
steeper
not
or
right. And this I don't understand how the toponium can give an explanation, because the toponium somewhat sits in one place. Well, it's true that the PT is everywhere, right, if you fix the MT. But I think the fair answer is I don't know, because I haven't looked at it. It's a good question. But I'm not, I don't know, I'm not super adamant.
Me neither.
Okay. Yeah.
My questions are probably very stupid. So the first is, are we sure that entanglement can be computed perturbatively? So do you expect that higher order corrections can't move this by much?
Yeah. Yeah, so.
Because higher order corrections, you have the real emission, so you have other states that can wash out the entanglement.
Yeah, so in TT bar, we have the Monte Carlos, apart from the toponium. Now, our Monte Carlos TT bar have spin correlation up to NLO, and in fact, the full Monte Carlo up to NLO, and then NLO prediction is a differential, not Monte Carlo, but differential, and NNLO. So we know the spin density matrix up to NNLO in QCD and electron weak. So we know that the entries of the spin density matrix in TT bar are not greatly affected NNLO. NNLO, there is one exception, but then it's stable in NNLO. So the perturbative prediction for the density matrix, which is what we use in the end, is stable under relative correction. This we know since Bernreuter calculation in the before 2010. Then it's been improved, but this we have even in powering and MC10LO. So this we know. The effects on radiation, if you are inclusive enough, are not very large in the TT bar. Now, we and the group in Milano, with Giovanni Pelliccioni, Vicini, and so on, we did a recent computation on the effect of electroweak correction in the spin correlation in X into WW. So now there are Q-threads, system is more complicated, violation of Bell inequalities and entanglement are difficult, but so you analyze your system, and what they found, and what we found and confirmed, is that the effect of electroweak corrections on some of the entries of the correlation matrix are enormous. Okay? Which means that some of these coefficients are not stable. Well, the way we extract this coefficient through quantum tomography is not reliable, let me say it that way. Okay, so that actually is very exciting. So, I mean, could be negative result. It turns out that it's not a negative result, because there are ways of building a marker which is not including these unknown, these non-stable terms. So this is a paper that we will send soon, but the information is already in the Pelliccioli-Vicini paper. So this is a question that we are studying very well, effectively with the Monte Carlo, and we are also studying it theoretically now. I mean, like from quantum information point of view, if there is a way of describing the system with this formalism, not exactly this one, keeping into account external radiation. and there is. So it's very interesting. Thank you for your question.
More questions or comments? No? Okay, then thank you very much, Fabio.
Thank you.
As usual, there are refreshments outside.